Welcome back, everybody. Here's a different kind of decay that we're going to cover. Mn here is the symbol for manganese. It's not magnesium. Magnesium is Mg. So this is a different element called manganese. And this particular manganese is manganese 49 because that's its mass number. And I'm going to tell you that manganese 49 is unstable. If you wait around long enough, something amazing is going to happen in that area over there. Well, what happened? Let's watch that again. This little red plus thing here, that's a proton. And what happens? Well, it turns into a gray thing. That's a neutron. That's my cartoon for neutron. This little red dot as well. Now, the little red dot we have not covered in this course yet. It kind of looks like an electron, but in my course, the electrons are colored blue, and that certainly ain't blue. So what is it? Well, this thing is called a positron. Sometimes it's called an anti-electron. A positron has all the features that an electron has, same weight, same things like that. The only thing different is that it has a positive electrical charge instead of a negative electrical charge. What you're going to see is that the positron is not happy being there either. And guess what's going to happen? It gets fired off into the distance. So we're going to write the decay equation for manganese 49 decaying. Well, it fires off a positron. So believe it or not, this is how you write the symbol for a positron. You write E for positron, lowercase e, right? That's a joke. Well, it's not really a joke because that is what you write. That thing has the same weight as an electron. So we're going to put a 0 in the upper left because that's the mass number for an electron. In the lower left, well, it did have a positive charge. So with an electron, we would have written a negative 1 here. But with a positron, we're going to write a positive 1. We write the lowercase e because it's similar to an electron, has a mass number of 0, but the positron has a charge of +1. So this is how you write positron in chemistry. And then whatever this thing is, it is not manganese anymore. But we can play the same game and figure out what it is. Everything on the left side of the arrow has a mass number of 49 that totals up to 49. Everything on the right side has to have mass numbers that total up to 49. Positron has no mass number, so our question mark has to have a mass number of 49. Manganese has 25 protons, which means it has 25 positive charges. That's the only thing we have on the left side, so everything on the right side has to add up to 25 positive charges. Well, the positron took one of the positive charges, so our question mark has to have 24 positive charges. If you look up who in the periodic table has 24 positive charges, you're going to see it's a kind of atom called chromium. And the chromium symbol is capital C with a lowercase r. So this is just another kind of decay. For reasons that I have no idea about, you might think that this should be called positron decay or something like that, but for whatever reason, it's called positron emission. So basically, the positron gets fired off into the distance, and this time they wanted to tell you that, but I guess you already knew that. But that's usually what it's called. You may have heard of PET scans. PET scans are something that get done in healthcare where people look for cancers and types of things. PET scans are a type of imaging that can be done on people to look for things like tumors. The P and the E in PET scan stands for positron emission. And just in case you care, I can tell you a little bit about how PET scans work. PET scans basically, what they usually do if you're going to get a PET scan is they will feed you some type of sugar or something related to a sugar that is emitting positrons, that is firing off positrons. And the sugars usually go to different tissues in your body that need a lot of energy because sugar can give you energy. So these sugars that are firing off positrons go all over your body, but they kind of congregate more in areas that need a lot of energy. So sometimes tumors need a lot of energy because they need to grow. And so if you have a tumor, this sugar that's firing off positrons might show up in tissues that are tumorous. And what happens is after they give you this sugar that's firing off positrons, they put you in front of a detector. Here's you. And maybe you have a tumor here. and the sugar is firing off positrons, and there's a detector, and the detector can figure out where the positrons are coming from. They say, oh, there's some positrons coming from here, which is where they don't normally come from. Maybe that's a tumor. That's basically what PET scans are doing. The worst drawing ever. Here is a different kind of decay. This is another unstable isotope. Tc stands for an element called technetium, and this one is a little bit weird. Works basically the same way. We split the equation down the arrow. Everything on the left side weighs 99, so everything on the right side has to add up to a weight of 99. This thing already has a weight of 99, so how much does our question mark weigh? Well, it's got to weigh 0. Technetium, if you look it up in the periodic table, has 43 protons, so it has 43 positive charges. It decays into technetium, which we already said has 43 positive charges, so everything on the right side has to add up to 43 because everything on the left side adds up to 43. This technetium already has 43, so how many positive charges does our question mark have? It's got to have 0. So whatever our question mark is, it has a mass number of 0, and it has no positive charges. Now, this one you can't look up in the periodic table because there is nothing written in the periodic table that has no positive charges. So I'm just going to tell you what it is. What you write in this case is you write the Greek letter gamma, which I said in a previous video looks like a ribbon kind of upside down. Now, I don't really care that you know what the symbol is here, that it should be a gamma. I don't expect you to know that. On a quiz or a test, if I gave you this type of problem, as long as you could figure out the top and bottom numbers, then you would have answered the question correctly. Now, this particular type of decay, well, it's called gamma decay, and this is the one that they found third. Now, many of you are probably looking at this and saying, what the French toast, right? Technetium-99 turns into technetium-99. Does that even make sense? And it fires off this thing called gamma that weighs nothing and has no positive charges? Well, this thing here is called a gamma ray, and it has a lot of energy that gets fired off. The weird thing here is this M. The M stands for metastable. You don't really need to know this, but I'm just trying to explain the equation to you. Metastable means kind of stable, but not super stable. So what metastable is telling you, what this M is telling you is this particular technetium atom has a little bit of extra energy, and that's what makes it not super stable. If you wait around long enough, it turns into a technetium that doesn't have that little bit of extra energy, so it's more stable. But the extra energy that it used to have, it got fired off into the distance as a gamma ray. So this is just another type of decay, a little bit weird because you can't necessarily guess what that symbol is. But you can definitely figure out what the numbers are for that, and that's all I expect you to be able to do for those types of decays. Now, this is a table here that shows you some of the stuff that we've already talked about. So we talked about alpha decay. That's when you fire off a helium that has a mass number of 4. We talked about beta decay. That's when you fire off an electron. We talked about positron emission. That's when you fire off a positron. We just did gamma decay. That's when you fire off a gamma ray. What this table is supposed to show you is that these are not the only kind of decays that exist. You can also fire off a proton. You can fire off a neutron. And you can fire off all sorts of other stuff. Even this table is not a complete list of things that can get fired off, but it's just to show you that there's all sorts of unstable isotopes and things that can get fired off from unstable isotopes. So what do I expect you to be able to do? I expect you to be able to look at an equation like this, where there's one missing piece, and you should be able to find what the missing piece is. At the very least, you should be able to figure out what the numbers are in the upper left and the lower left. The other thing that I want to point out is I can move this question mark around. It doesn't always have to be here. I could hide this part off to the right, and you should still be able to figure it out. And, in fact, I can even hide the stuff on the left side, and you should still be able to figure it out. So, for example, if I hid the stuff on the left, you would look at the right side and you say, oh, top numbers on the right side add up to 49, so this must be 49. And then you would figure out the bottom number for chromium. I think that's a 24. And you'd add up the bottom numbers. 24 plus positive 1, that's 25. So this is 25. You look up who's got 25 positive charges. You say, oh yeah, that's my friend manganese. So there's the completed decay equation. So it doesn't matter where I put the question mark, you should still be able to find it as long as there's only one missing piece. And that's the end of this video. See you in the next one.
It's the drink that you don't pour. Now when you take one sip, you won't need any more. As small as a beetle, or big as a wheel. Boom, atomic cocktail. Falls a splash all around the place. When you see it coming, just grab your suitcase. It'll send you through the skies like air mail.